So good evening, everyone. So thank you for coming. So today we'll have our chat to give us a talk about high nuclear experiment. So Chad graduated with his bachelor in physics in 2016 from UC Berkeley, and then just joined us just in 2016, right? And then he studied experimental nuclear physics under Jolie Szewski. I don't know how to pronounce it.
Yeah.
Okay, and Chad is a member of the Goddess and Aruba collaborations, and he has been in residence at Oak Ridge National Lab since 2018. And apart from research, he enjoys running long distances. If Steven and Chad, you can go together and play guitar. Yeah, we can play guitar together, maybe. And saxophones, and as loud as his neighbors. Yeah, he's just like kind of good neighbors. And yeah, so that's it. So maybe we can first unmute ourselves a bit and give Chad a big hand and give yourself a big hand for coming. So yeah, Chad, take it away.
Okay, yeah, thanks so much. Let me share my screen here. Okay. All right. I'm in a presentation mode. Cool. Okay, so yeah, so I'm Chad. Let me change the pointer here. And yeah, so as Tsung-Chi mentioned, I've been in residence at Oak Ridge National Lab for the last 2 years. And this measurement I'm going to talk about, this carbon-13-DN nitrogen-14 reaction. Let me get rid of this thing here if I can. There we go. This carbon-13-DN nitrogen-14 reaction that I'm going to talk about. This was actually measured the first summer I spent out there between my first and second year, so 2017. And for the last 3+ years now, it's been kind of this nagging side project that I really wanted to get finished. And finally, in COVID world, I've actually had kind of the time to sit down and hammer out most of the analysis on this and actually get some nice preliminary results that I can show. So that's what I'm going to talk about. And I've the fun title of this talk is Watch Your Background, because this carbon-13-DN reaction, really what it is, it forms a kind of nasty and previously unknown background for measurements of a more interesting reaction, which are particularly pursued in underground facilities. And I'll talk about that. So I can advance my slides, cool. So to zoom kind of all the way out, the question and kind of the big picture, the question I would say that I'm most interested in helping to answer, and I would venture to guess most low energy nuclear physics experimentalists like me are most interested in trying to help answer, is the question of where the chemical elements come from and how they're made in the universe cosmologically. So this is a nice little cartoon from Wikipedia of the periodic table, and the different elements are color-coded based on their cosmological origin. So to get a little bit more specific, we think we have a very good handle on how light elements are made. And by light, I mean lighter than the iron peak. So iron peak is iron, cobalt, nickel, manganese, kind of those elements. So we know hydrogen, helium, and lithium, those are produced in, most of that is produced in the Big Bang. And then elements heavier than lithium up to around the iron peak is primarily made via fusion in stars. So this is a plot of average binding energy per nucleon of different isotopes as a function of nucleon number. And it's actually peaked at iron 56. And this is really important. What this means is that fusion, as you're fusing things up to iron 56, you get energy that comes out. So in a star, stars use that nuclear energy from fusion to as part of how they resist gravitational collapse. But when you start pushing beyond iron 56, it now costs energy to fuse and make heavier stuff, which of course we observe. So stars can't do this, and that means there needs to be a mechanism other than charged particle fusion, or mechanisms that are responsible for the synthesis of heavier elements. And we can get some clues about this if we look at this plot. This is a plot of the abundances of elements as a function of atomic mass in the solar system. And so here's the iron peak here. And then out here, there are actually 5 peaks that I've got arrows pointed to. And the hope is that that structure, that very kind of unique structure, will give us some clues about what's going on. So it turns out we believe to a pretty good level of confidence that neutron capture via 2 processes called the S and R process is responsible for nearly 100% of all heavy element synthesis, heavier than iron. And this is because neutrons are electrically neutral, so of course there's no Coulomb barrier opposing fusion as you would trying to smash 2 charged particles together. So this is the plot. This chart is what we call the chart of Nuclides. It's essentially just an extension of the periodic table to include neutron number on the x-axis, and so you have proton number on the y-axis. And your stable isotopes are these black squares here. And there's a bunch of different arrows that have been drawn on here at this plot. If you go to a nuclear physics conference and you watch low energy talks, you'll see this plot pop up in almost every talk with all these different arrows drawn on it. And those are different nucleosynthetic processes. So the S and R processes are neutron capture processes. And what happens in both is you have seed nuclei, and they capture neutrons, and they beta decay back to stability. But those neutron captures and beta decays happen on vastly different timescales. So the slow neutron capture process, or S process, is this magenta arrow. In that process, the neutron capture, the average neutron capture time is quite long, and it's much shorter than the beta decay lifetime of any unstable isotopes produced. So what happens in the S process is you capture a neutron, beta decay back to stability, and do that over and over again. You stay right alongside the valley of stability, as we call it. The R process is this purple arrow. It's way out here in this very neutron-rich region. And in the R process, what happens is you capture a lot of neutrons very quickly, and only at certain points do you beta decay back to stability. The neutron capture time is much, much shorter than the beta decay lifetime. So if we go back to our abundance plot, it turns out that the peaks we see in this plot correspond really well with what we call the neutron magic numbers, specifically to the n equals 50, 82, and 126. And these magic numbers are due to the fact that, to a good degree, atomic nuclei actually have a shell orbital structure that you can use to describe them. And so these are where kind of the orbital closures, or the shell closures, are. So it turns out that strontium, the most common isotope of strontium, if we look at the S process first, the most common isotope of strontium has 50 neutrons. Barium has 82 neutrons, and lead is 126 neutrons. And so S process lines up pretty much bang on with those neutron numbers. The R process, those peaks are shifted to the left a little bit, and that's because in the R process, when you hit these magic numbers, you're in a much more neutron-rich region, so you have fewer protons. So the atomic number of those peaks is a little bit lower. And then there's also this peak at europium, which is due to something entirely different, which I won't go into, but feel free to ask. So back to talking about the S&R processes. So these were theorized kind of as their own separate, distinct, and wholly contained processes, but we now believe that each of these has some sort of component structure. So the S process, we're pretty certain, has 2 branches. There's a main branch that occurs in thermally pulsing asymptotic giant branch stars, and there's a weak S process that occurs in the cores of massive, and by massive I mean greater than 8 solar mass stars. The R process, we're now starting to think, may have multiple sites as well. So there is something called a hot R process that we think may be occurring in a specific subset of core collapse supernovae. And then there's a cold R process, which we believe we observed back in 2017 in merging neutron stars.
Can I ask a question?
Yes, yeah.
So I've kind of first, so this S and R process. So you say for this stable nuclei,
Yes.
I kind of lost that. So you say they are going through this S process, or
Yeah.
oh,
So yeah. So the state in this chart, the chart of nuclides, the stable nuclei are in black, and then yeah, to explain it a little better, in light gray, these are unstable nuclei that we've studied in the laboratory in some form. And then in dark gray, these are actually kind of, figment. These are a figment of a theorist's imagination. These are, something some theorists. These are nuclei some theorist thinks, might exist, at least for some short lifetime. And you can see that our process goes right through it. Yeah.
I see.
So, but yeah, they all start right around the iron peak down here. So you have seed nuclei, stable seed nuclei, and the S process, you neutron capture and beta decay, and you stay right alongside the valley of stability because you're not neutron capturing very quickly. Whereas in the R process, you have a much higher flux of neutrons. So you shoot way out here into this very neutron-rich region.
Can you say again? Oh, okay. It's kind of a basic question. So why the iron is kind of the important one?
Yeah, so that goes back to here. So iron is, or iron peak specifically, because you can kind of push beyond it. But those are the heaviest elements that stars can make via fusion. And so typically these processes, so a lot of these, so the R process specifically happens, at the death phase of a star. So kind of the heaviest stable elements that have stuck around to that point are iron and in that region. So those are, we call those, I mean, any stable thing sticking around can be a seed nucleus, but the heaviest stuff is in that iron peak region. And of course, and this is also true, not for the youngest stars, but as material gets recycled into the interstellar medium, you'll have heavy elements like iron and cobalt and stuff that'll stick around, and it can serve as seed nuclei for the S process, for both the main and weak S process.
Okay.
Yeah.
So you say like this believed to occur in, so that means it's still kind of debatable. And so how to kind of know the origin of that? What's the experiment to
right. So for example, the R process, we're pretty sure, although it's still somewhat an open question, we think we saw R process elements in the neutron star merger that happened in 2017. That was observed by LIGO and Virgo. And the way you'd look for this is you can do it spectroscopically. So you can look for what we call a kilonova, and it's a flash of gamma rays and X-rays that would occur in this event, where you have very unstable stuff being produced, and that likes to beta decay and gamma decay, and so you can look for all those gamma rays.
Oh, I see. Yeah. Got you. Thanks.
Yeah. Okay, yeah, so I talked about how the S process, the neutron capture time is much smaller than the beta decay lifetime. So stable isotopes are shaded here, and you never have neutron capture really on an unstable isotope. It almost always beta decays back to stability before you capture another neutron. And so, yeah, I should mention, by the way, that this measurement that I'm talking about, it's principally concerned with the S process. So I talked about how the S process occurs during helium shell flashes in thermally pulsing asymptotic giant branch stars. And I think this is a cool illustration of that. This is a MESA simulation that I found on YouTube. This is just a one solar mass star. And so you can watch it evolve in real time, which I think is cool. Or not in real time, sorry, in very sped up time. And so, your star forms, you start having hydrogen burning in the core. And then eventually that hydrogen burning moves out to a shell, and you start depositing helium in the core, which eventually will ignite. Then that helium burning will move to a shell. So you have hydrogen burning in a shell and helium burning in a more inner shell, and you're depositing carbon and oxygen, the products of that helium burning, in the core. Right, and what actually happens here is helium burning proceeds much more quickly than hydrogen burning. And so in that shell, you eventually exhaust all of that helium fuel, but hydrogen burning is going to deposit fuel in that shell. So you exhaust the fuel, but then you get more and it ignites again, and you get this pulsing that's going to happen. And you can see that here. You can see the helium burning kind of flashing on and off over and over again, which I think is really cool. So if I can move on here, whoops, there we go. So this is a nice kind of diagram of what's going on. So you have your carbon-oxygen core and your AGB star. You have an inner shell of helium, and you have a convective envelope in the outer layers of hydrogen. And in the intermediate ranges, you can see where this helium flash occurs. It turns on at specific times and lasts for, a couple hundred years or so. So what's happening here, kind of the reactions of interest are here when this helium flash occurs. You dredge up carbon-12, and various other things from the carbon-oxygen core. And that can come all the way up to this envelope where it can react with hydrogen with protons. And that makes nitrogen-13. Nitrogen-13 electron capture decays to form carbon-13. And that carbon-13 is, of course, going to fall back down, and it'll be in this helium inner shell in this helium burning region, and it can react with helium-4, or an alpha particle, to make oxygen-16 and a neutron. And it turns out this carbon-13 alpha N reaction is the primary source of neutrons for the main S process. And it results in a neutron flux somewhere between 10 to the 5 and 10 to the 11 neutrons per centimeter squared per second. And for a single nucleus, a neutron capture rate of about 1 neutron capture every 10 years. So really, really slow. And it takes on the order of thousands to 10,000s of years to complete. So very slow. So we've identified this carbon-13 alpha N reaction as our reaction of interest, the source of neutrons. So as nuclear physicists, as we get ready to go into the laboratory to an accelerator to actually measure this, to send a beam of alpha particles onto a carbon-13 target, we need to know what energy range matters. And the way we figure this out is using something called a Gamow peak, or a Gamow window. This is pretty straightforwardly, it's the product of two different probabilities. So you have your thermal Maxwell-Boltzmann distribution for carbon-13 and alpha particles in this star at a temperature of about 10 to the 8 Kelvin in this case. And then you have your probability for these two charged particles to tunnel through the Coulomb barrier and react. And of course, that's strongly dependent on energy, right? More energy equals a higher probability of tunneling. And so if you take the product of those two distributions, you get this Gamow peak structure here, which has a peak energy, and it has this full width half maximum, which we call the Gamow window. So for carbon-13 alpha N at about 10 to the 8 Kelvin, this peak energy is about 190 keV roughly, and the window is from about, again, very roughly 140 to 230 keV. So this is a plot of nearly all measurements of the carbon-13 alpha N cross-section to date. And I've kind of, as a fuzzy box, I've put the Gamow window here. But the lowest energy to date was made by Drotlev et al. In 1993 at 279 keV. So about 50 keV above the edge of the Gamow window, more or less. So it's useful visually, at least, to kind of recast the cross-section as something called an S factor. And the equation for that's here. You can sort of think of this as taking the cross-section and removing all the Coulomb dependence. And so you're left kind of with the pure nuclear physics, more or less, is kind of the hand-wavy explanation. And if I do that, this is the same plot. This is all existing data to date, the existing results. You can see a lot of these low energy measurements have really large error bars. And I say that not as a knock on any of these experimentalists, because this is a really hard, tough reaction to measure for reasons I'll get into. But nonetheless, these large error bars are a problem because we want to understand the S factor. We'd like to know the value of the S factor within the Gamow window. And sans having actual data within the Gamow window, typically we would extrapolate existing data. But of course, that's hard to do when you have limited constraint due to these large error bars. And additionally, there's a state in oxygen-17. And so oxygen-17 is the compound system for carbon-13 plus helium-4. So there's a state which leads to a resonance, or will lead to a resonance in this reaction. And you can start to see the data tracking up, indicating that that might indeed be the case. but we have no idea what that those resonance parameters look like. We've not studied it in this reaction, so we can't make very solid predictions about it. And so there's a couple extrapolations in here. Green is if you don't consider any effects of that resonance at all, and red is if you try to include some estimated resonance effects, and there's some upper and lower error bands on that. And you can see those error bands are gigantic. So really, we need more measurements of the carbon-13 alpha in cross-section at low energies. And of course, ideally, yes, yeah.
Also, so from there are 4 curves. So which one, I mean, can they be theoretically predicted? Like which one should be the most possible one, or no?
Yes, so this, sorry, so there's really 2 curves. The green is if you don't, so we know that there's a state in the compound system at center of mass energy of -2 ± 8 keV. So we know there should be a resonance over here. And we don't know much about it. So this is if you ignore anything about the resonance and you just try to extrapolate based on the data. Red is the solid red line is if you kind of estimate kind of the effects, the parameters of this resonance and extrapolate that way. And then the dashed lines are upper and lower bands.
So just we don't know like how strong the coupling. So we cannot sure like is the top curve or the bottom curve or the middle one.
Yeah, we don't know how strong the resonance is. We don't know its width. Exactly.
Gotcha.
We don't exactly know its energy in the center of mass frame, right? The state isn't particularly well known. So there's a whole bunch of problems that have yet to be studied. And of course, the best way to study a resonance you can look at other reactions forming this compound system, but the best way to study a resonance in your reaction is to look at this reaction of interest specifically. So we need more measurements of carbon-13 alpha, and ideally, of course, it'd be great to do it within the Gamow window. But sans that, it's still useful to measure it above the Gamow window. And if you can cut down these errors a significant amount, that's still tremendously useful because it constrains this extrapolation a great deal.
Can I ask a question?
Yeah, of course.
So in the last slide that you had, it seemed that at high energies, the theoretical predictions are strictly lower than what you see in experiment. I can't see the error bars too well.
Right, yes. Yeah, there's no...
Is that a problem with theory, or is that just within the range of the error bars?
It does look like it overlaps a little bit, but you're right, it's a little lower. Yeah, this fit, I believe, it's to not go into too much detail, this is something that we call R matrix theory, and it's using the kind of scattering R matrix and extending it to nuclear reactions. So yeah, it's not uncommon to see kind of slight under predictions or over predictions when you do this. Yeah, this is, I mean, having seen a lot of these, I would call this reasonably good, actually. Yeah, but you're right, it's a little bit low. And, yeah.
Can I ask another question? Okay,
sure, yeah.
kind of. So, so the goal here is to know how much like the coupling is this resonance effects. How much is that? So, and then,
right.
My next question is, why we care? I mean, how can this resonance? I mean, are there any other things this can tell us? Just say how we.
Yeah, we just care what the value of the S factor is in this energy range. And we don't really have a good way to predict that right now. So that's, yeah, so we want to know what this reaction rate is in this range of energies, because that tells us how many neutrons will come out of this reaction in a star environment.
So this might help us to solve other problems. I think that's what I kind of want to.
Oh, it's sort of, I mean, yeah, it's got a pretty specific application. There's other applications that this reaction is useful, especially at higher energies. So much way to the right of this plot. Becca actually knows a fair bit about that. But at least in these low energies, we're really trying to just constrain this reaction rate so that we know, yeah, it's really just a matter of knowing how many neutrons come out of this reaction at this temperature in this type of star.
Okay.
Yeah.
Great.
Whether you care about that or not is, yeah, I suppose up to you.
Yeah, sure.
Yeah, I mean, a lot of nuclear astrophysics measurements like this, I had someone disparagingly describe it to me as making small tweaks on things we've already sort of predicted, which is true. But nonetheless, we get funded to do experiments like this, so I guess why
that's
not
still
do them
important.
and do the best we can. Yeah,
that's still important. Sure.
All right, so so I mentioned how this this reaction it has very low yields, and a lot of the accelerators that this would be measured at have beam currents for alpha particles on the order of hundreds of microamps. So that's like 10 to the 14, 10 to the 15 particles per second. So really intense. But even at that, of course, the reaction cross section is dropping really quickly with decreasing energy because of the Coulomb barrier. And so what happens is often your detected events, when your yields are really low, your detected events are going to be dominated by background of natural and cosmic ray origin. So this is a really nice plot. Black is the background you might see at a laboratory at sea level. Green is the background you would see if you went 1,400 feet underground. And blue is the background you would see if you added a little, some full shielding to your setup. So even with minimal shielding, you have a 2 order of magnitude improvement. So this is a pretty good solution to actually just build a very high intensity accelerator laboratory deep underground. And there's 2 such facilities in the world right now that do this. There's LUNA, the Laboratory for Underground Nuclear Astrophysics at Gran Sasso National Lab in Italy. And then in the US, there's CASPAR, the Compact Accelerator System for Performing Astrophysical Research. And CASPAR is located at the Sanford Underground Research Facility in South Dakota at the former Homestake mine. So these are mine shafts here. And Sanford SURF houses a bunch of other different interesting experiments, a lot of neutrino experiments. But there's CASPAR sitting down there. And it's a 1 megavolt tandem Van de Graaff that was installed in 2016, and they achieved first beam in 2017. And I have seen preliminary results at conferences. I don't think they've published anything yet, but I would assume that that's forthcoming pretty soon. Now, back in 2016, Mike Fabraro, who was at Oak Ridge National Lab, presumably thought to himself and had the very crazy idea of what if we measured this reaction above ground and just used as much shielding as we could possibly come up with. So this is their setup. This is, and I'm going to talk, by the way, I'm going to talk a lot about this measurement that was done at Oak Ridge. And I participated in it minimally, but it's really the work of Mike Fabraro and Becca Toomey, who's here at Rutgers and who's listening in. So it's really their work, but I think it's important for me to talk about it and show some of their preliminary results because therein lies the motivation for my work. So this is the target, and these are their detectors, which I'll talk about in a second. They completely surrounded these with water bricks. So these are bricks contained with water, filled with water. And this is to shield from outside background neutrons. So neutrons are really hard to stop. They tend to pass through everything because they're electrically neutral. So the best way to actually stop neutrons is the thing that has the highest scattering cross-section for neutrons is protons. So something with a lot of hydrogen in it, like water or high-density polyethylene pellets, which they filled the spaces with, that's the best way to shield against neutrons. So this is their setup, and it's about 600 pounds of shielding, which is a lot. And then above this entire setup, they placed these 3 plastic scintillators, these big paddles. And these served as active cosmic ray vetoes. So the idea is this sits above everything. If you have a muon that comes in, it should hit one of these detectors and you'll get a signal. And you set up your data acquisition to go, aha, that's a cosmic ray. I don't want to record anything that's going on in here right now. So that's what we call active shielding. Excuse me. This experiment was done at the Multicharged Ion Research Facility, or MIRF, which was an atomic physics facility at Oak Ridge National Lab and will be an atomic physics facility again. It's currently dismantled and moving to a new location because there was another group at Oak Ridge that had more money and wanted the building. But anyway, we realized that this ECR ion source on this high voltage platform was a really good high intensity ion source for doing low energy nuclear physics experiments with light ions. So there's our nuclear astrophysics test table right there. So I need to take a brief aside, and I need to talk about neutron detection and ways to detect neutrons. Because neutrons are really tough to detect because they are electrically neutral and they are not ionizing radiation. So like I said, they like to just pass through everything. So one way to count neutrons is using something called a proportional counter. An example of this is habanero, which is this beast thing here, which typically lives at the National Superconducting Cyclotron Laboratory in Michigan. So proportional counters, they're typically constructed from helium-3, which has a really high absorption cross-section for thermal, which is order of 0.025 electron volt neutrons. Now, of course, in your reaction, you've got neutrons of a lot of very high energies coming out, you know, keV, MeV neutrons. You need to slow them down so that they can capture on the helium-3. This is called thermalizing them. And you do this with a moderator, which is typically polyethylene. So you can see here in habanero, it's a big block of polyethylene. And in these holes, you have tubes that contain helium-3. So this method has compared to other methods, it has a very high efficiency for counting neutrons, but this whole thermalization process, it destroys any information you had about the neutron energies. But nonetheless, if you have a reaction and all you need to do is count how many neutrons are coming out of it, all you need to do is count how many neutrons are coming out, then this is by far the method of choice. So you can imagine what an underground facility like Luna or Caspar might be using to detect neutrons from the carbon-13 alpha in reaction. If you need to know something about the energy of your neutron, you can use time of flight spectroscopy. So this is VANDAL, the versatile array of neutron detectors at low energy. This is owned by the University of Tennessee, Knoxville. The way this works, you place your detectors some distance L from your target, and you measure the time. You measure the time of flight, the time difference between a signal in your detectors and a beam pulse. And that's important. You have to use a pulsed beam. You have to have some ACU time structure to your beam. So you can't run a high current DC beam. But if you measure that time current, you can kinematically infer your neutron energy. Now, of course, more distance means better energy resolution, but it means you have less solid angle coverage and less efficiency. So you have a trade-off there. The last thing I'm going to talk about is spectroscopy, direct spectroscopy, or quasi-spectroscopy. I've got in parentheses there, and I'll explain the difference. The goal with this method is your neutron comes out, and you would like the neutron to deposit all of its energy within your detector volume. So an example of a quasi-spectroscopic array is SABRE, which you may have seen this photo a couple slides ago when I was showing the setup for the measurement at Oak Ridge. So SABRE is the scintillation array of bars for reaction experiments at Oak Ridge National Lab. It's 5 liquid xylene-based scintillators arranged in the barrel configuration. There's a single detector there. So the idea is the neutron comes in, it deposits all of its energy in the detector. You read that out as some signal, and you can either use that signal as a corollary for the neutron energy. So that's the quasi part of this. Or if you really need to know the exact neutron energy, you can do what's called unfold the spectrum from the detector system. And this, these are advanced analytical techniques that Mike and Becca have been working really hard on. The nice thing about this sort of array is you can place your detectors anywhere, including very close packed high efficiency geometries without a sacrifice in energy resolution. So that's really cool. Another nice thing about SABRE is we can do particle identification using something called pulse shape discrimination. So this is a consequence of the fact that the light output in a detector for a neutron and a gamma ray in an organic material has a very different slow component. So neutrons have a much longer tail than gamma rays. So if you take 2 different integrals over your light signal, one over the entire signal, and then a short integral over just the tail, you can construct a PSD parameter, we call it, which is the ratio of the 2. And so this is what it looks like in practice. This is actually from that measurement. This is at a beam energy of 500 keV. You can see they have a very well populated band of gamma ray events and a very sparsely populated band of neutron events. And there's a few gates on here that I want to talk about. So they have a 3 sigma limit on the neutron band, and they figured that out by putting a californium-252 source, which emits a lot of neutrons, in the middle of the array. And then you get a well-populated band, and you could set these 3 sigma limits. And then in light response, which again is a corollary for neutron energy in this case, this lower limit is the resolution limit of the detectors. And this upper limit is called the Q value limit. And this corresponds to, at this beam energy, this is the maximum possible energy that a neutron can come out of that reaction. So you should not be seeing neutrons with an energy higher than a light response corresponding to 1,000 keV electron equivalent. But you very quickly see that there are 8 neutrons up here with higher energies. And that's a problem. We need to know where those are coming from. This is some background. And this could be a problem because it could be leading to additional events in our region of interest that we're blind to. So we need to understand where these neutrons are coming from. So it could be from something in our target that we don't know, or it could be from something in our beam that we don't expect. So accelerators separate ion species using something called an analyzing magnet. And how this works is you have a magnetic field perpendicular to the direction traveled by your ions. And this causes them to follow a circular path proportional to their mass to charge ratio. So if you know what you want to come through, you can tune your magnetic field accordingly. Now the problem is alpha particles have a mass to charge ratio of 4/2, and deuterons have a mass to charge ratio of 2/1. So they have the same mass to charge ratio. So if you get deuterium in your beam, there's no way to get it out. You can be fancy if you have the ability to do this. I highly encourage you to do so. You can be fancy and you can use singly ionized helium-4 instead of a doubly ionized alpha particle. So 4/1, but you still have overlap with molecular D2+. And I should stress all this deuterium, should it be in your system, that's coming from leaks from the air, which are of course small. And then hydrogen is a small component of air. And then D2 is a small component of all total hydrogen. So you get very, very little of this. But nonetheless, this is a potential problem, and most facilities actually don't really know how much deuterium they have in their beamline and their alpha beamlines. I dug through the literature, and Luna actually has an estimate. They say that the ratio of deuterons to alphas is less than or equal to 10 to the -7. So again, a very, very small number, and you would be forgiven for assuming that that's, plenty and it's suppressed well enough. The problem is the deuterium in the beamline, it's going to react with the carbon-13 target via the carbon-13 DN nitrogen-14 reaction. And if I compare in these data points up here, these are measurements of the carbon-13 alpha N oxygen-16 reaction, and there's a fit to those data points in red. And then down here in orange, that's a measurement of the carbon-13 DN reaction with a fit in black, and that is suppressed by 10 to the -7. And these vertical bars, these black vertical bars I've plotted here, that's actually the Gamow window for the alpha N reaction. And you can see, even suppressed by 10 to the -7, carbon-13 DN, this background reaction starts to actually dominate. So you have more background than your actual signal of interest. And this is really a bad thing because, as I mentioned, proportional counters, which all these facilities are using, they don't know anything about neutron energy. The only reason we suspected this at all is by using a quasi-spectroscopic approach with SABRE. So other facilities that aren't doing that, they're completely blind to whether their neutrons are coming from carbon-13 alpha N or carbon-13 DN. And so that's a big problem. They're potentially over-predicting their cross-section by quite a large amount. So what we need to measure the carbon-13 DN cross-section at low energy so that we can subtract it from data on carbon-13 alpha N. So we went back to MIRF to do this. And I'm gonna skip that. This is a schematic of the beamline that Becca put together and I'm stealing. The ECR source, it's mounted on a high voltage platform. So you have a positive voltage platform and a positive ion, and so the ion will accelerate away from that. We can adjust that voltage up to a maximum of 250 kilovolts. So for deuterons, which are singly ionized, we have a maximum energy of 250 keV. As I mentioned, this source is like this one. We're capable of delivering a beam at a current of hundreds of microamps. And we actually started at about 100 microamps. And then the radiation safety guy at the lab came in and told us we had better take it down quickly or he was going to shut us down. So we ran at about an average current of 3 microamps, which was plenty for what we needed to do. The astute observer.
Question?
Oh yeah, sure.
Oh, sorry. Just few slides back. So you say other people cannot distinguish nitrogen 14 and oxygen 16. So why they cannot do so?
Well, they can't distinguish the. Typically, in an experiment like this, the only thing you see coming out is the neutrons. So these are usually thick target experiments. So the oxygen and the nitrogen usually stay embedded in the target, and you never see them at all. So all you see coming out is the neutrons. And as I mentioned, the method of choice for doing these experiments is using a proportional counter, and in which you lose all information about the energies of your neutrons. You only know how many neutrons came out. So if you have a large component of carbon-13 which is your background, you don't have any handle on how much of that there is, essentially. Right.
Yeah. Thanks.
Yeah, of course. So anyway, so yeah, the astute observer. So back to MIRF. We did this at MIRF. The astute observer might notice. Yes.
Just a question. So, I mean, 100 microamps, right? So the amps in your case, you're like thinking really in terms of like currents. So it's like the amount of like particles you're sending per second, right? Really?
Right. Yeah. Exactly.
Okay. So is it still like when you're running at 3 microamps like that? Do you have to like really measure for a long time to get all the data you needed?
This reaction was a lot easier to measure. So
Okay.
So the lowest energy steps at which the reaction was the rate was the lowest. We measured, I think the longest we measured was 2 hours. So pretty straightforward.
Okay, that's pretty short. Yeah, that's pretty short.
Yeah,
that's good.
This was in terms of nuclear, low energy nuclear physics experiments. This was a very short, quick experiment.
Cool. Thanks.
So for example, the alpha N measurement that Becca and Mike did, that was a really long measurement. I think that took them a few months to do all the energy steps that they did.
Yeah, so if you're interested, Victor, the lowest energy point that we did on the alpha N took an entire month of running for 16 hours a day to get enough statistics to get the last energy point.
Is that because the reaction is like so rare that you have to just get so much data point to eventually get it? Is that why?
Yes. Yeah.
Okay.
Wow.
Yeah, so it really it completely depends on what your cross section is, and that that directly affects how much time you spend to get the statistics that you want. So anyway, so yeah, there's 2 ion sources actually at MIRF. There's this Caprice ECR ion source up at the corner, and we did this to fabricate our carbon-13 targets. So the targets are gold-plated copper discs. And the way we made them is we sent a beam of carbon-13 straight into them, which implanted, and that's how we made our targets. And then even at just a couple microamps, the beam is actually hot enough to melt a hole right through these. So to prevent that, we actually water cooled the targets. And so this is the target holder. This is the back of that holder, and you can see the water cooling grooves there. And then this is the fully assembled holder, and you can see the water lines to and from.
Is this homemade?
Yes. Well, this is designed in-house. Mike Fabaro is responsible for all this, I think. I think he actually made this. He did. Made this when he was doing his PhD at the University of Michigan, and he brought it out. And he brought it out to Oak Ridge when he took his postdoc out there. So, and now he's staff at Oak Ridge, of course. But But yeah, this was all designed and fabricated by Mike Burrow. So I owe a lot to him for being able to do this work. For detectors, we used these 16 sodium iodide, thallium-doped sodium iodide scintillators. Fun story, these are actually radiation portal monitor detectors. So the Department of Homeland Security bought a whole bunch of these with the idea of sticking them next to train tracks and truck lines and stuff and using them to try to monitor for nuclear material being transported illegally. It turns out that these detectors really hate temperature changes, and they did not work very well as intended. So DHS had already bought a ton of these, and they sold them off for cheap. And so we acquired a bunch of them, or Oak Ridge acquired a bunch of them before I arrived. And it turns out they worked really well for what we needed to do. So we used them to detect.
You mean DOE bought it from DHS?
Yeah, exactly. Yeah. Yeah, but yeah, so we use these to detect secondary gamma rays from the carbon-13 DN gamma nitrogen-14 reaction. So gamma rays from the decay of excited nitrogen-14 that is produced in the carbon-13 DN reaction. And the reason we did this rather than just detecting neutrons is because this is one way to discriminate between carbon-13 alpha n, which always goes straight to the ground state. There's no gamma ray principally emitted in this reaction itself. Discriminate between that and carbon-13 DN is looking at these gamma rays, these characteristic sharp gamma rays from nitrogen-14. This is a nearly 4 pi array, amazingly, and 2 points that I'll go into is we're running in total absorption mode, and we can suppress background via something called event topography. Event topography is a really fancy name for a pretty simple procedure. If I divide my outer detectors, so this is a nice kind of schematic of the 16 detectors. If I divide this into 4 regions, VT, VB, VL, and VR, I can veto on those selectively. So a cosmic ray, it should always hit one of these top detectors. So I can place a veto on that. Some ground-based background should always hit one of the bottom detectors, so I can veto on that. And then maybe some cosmic rays are streaming across, and they have such a high energy that hopefully they hit both VL and VR, so I can place a veto on that combined signal as well. So a pretty simple procedure, and but it actually works wonders and cuts down a background. Good deal. Total absorption spectroscopy, what I mean by that is we have some time window. We trigger on a gamma ray event, and then we have some time window that follows, and we record all coincident events, and we sum them together. So the idea is, so this is the nitrogen-14 level scheme. These are the levels we can populate. So the ground state and the first 4 excited levels. So let's say, for example, we populate this 1+ state at 3948 keV. That state, 96% of the time, it likes to decay via a 1635 keV gamma ray and a 2313 keV gamma ray. So hopefully, we'd like to actually detect both of those. And if we do, we will sum those together to a single count at 3948. One nice consequence of this method is signals and energies that would otherwise be lost due to Compton scattering or electron-positron pair production of your gamma ray within your crystal. Those could be recovered, provided that you detect your scattered photons in neighboring crystals. So that's kind of a nice plus. To get a handle on the efficiency of this setup, because this is a large-ish array and we have some complicated event topography going on, the best way to get a handle on the efficiency is via simulation. And so we use a package called JANT4, which some other experimentalists listening in might be familiar with as well. But it's a Monte Carlo-based simulation package developed by CERN. And so there's our detectors. This is a wireframe view, and you can see the crystal, that rectangular prism crystal sitting within the detector volume. I can stack up the detectors, and then I can generate events. And this is a cobalt-60 source, which emits 2 gamma rays at 1.17 and 1.33 MeV. And you can see both those gamma rays interacting. Now, of course, your simulation is only good if it matches up to reality. So in blue, I have data that we took with a cobalt-60 source at MIRF in the middle of the array. And then in red, I have a simulation. And principally, I'm concerned with, how many single gamma ray events we have and how many summed gamma ray events we have. And you can see that the matchup is quite nice, at least in terms of the total counts in all of those peaks, or the relative intensities, I should say. I'm going to skip that. This we have, we can construct a single gamma ray total absorption efficiency for single gamma rays, but what I'm principally concerned with is my efficiency for detecting gamma rays in the cascade of excited levels in nitrogen-14. So I can tell Giant to make a nitrogen-14 nucleus at an excitation energy of 2313 keV, and it knows how to decay it. So you can see I get a lot of events from this single gamma ray at 2313 keV. Moving on up, 3948 keV is the next level. Here are my summed events. As I mentioned, this likes to decay via 2 gamma rays at 1635 keV and 2313 keV. And we actually don't usually detect the full cascade. We usually only get one of those gamma rays. And so what this means is incomplete summing can lead to the detection of a single 2313 keV gamma ray if we miss this 1635 keV gamma ray. And this is a problem because it looks identical to populating the 2313 keV level in our experimental data, right? When instead we populated this 3948 keV level. Luckily, I can quantify this contribution via this simulation. So I know if I see this many events at 3948 keV, I have this many bad events at 2313 keV, and I can subtract them. Moving on up through the levels, 4915 keV and 5106 keV, and that has a small contribution at 2313 keV as well that we need to be aware of. Finally, so this is our detectors set up around the target. This is with the top layer removed. We also had a neutron detector in there, a deuterated xylene-based detector. And this is the PSD spectrum in that detector. This was for a 15-minute run, just that single detector at a beam energy of 250 keV. We have a lot of gamma rays, as you can see, and we have a lot of neutrons coming out of this reaction. And if you compare to this spectrum that was taken over hours for the carbon-13 alpha N reaction with the entire SABRE array, you can see just how much of a problem, how much more intense the carbon-13 DN reaction is, how many more neutrons come out of that reaction.
Quick question, Chad.
Yes.
Did you? I just saw the neutron spectra. Was that was from the EJ301, right?
Yes, I assume I got the EJ301D.
Yeah. Sorry. I skipped out for a second. So that was. Did you ever try doing unfolding on that?
No. Yeah. No, we haven't.
No.
In fact, we haven't done anything in the analysis beyond this image here, and saying, "Oh,
that
there's
might
a
be
lot
worth doing because we could. Well, okay, yeah, we can talk about this later, but that might be worth doing just to see what it looks like.
Right. No, that's an interesting idea. But yeah, no, we haven't done anything with this other than saying, oh yeah, we have a lot of neutrons. See, but no, that's a cool idea. We'll have to talk more about that.
So Chad,
anyway,
is it a good thing here? Is it a good thing to have more neutrons than in the other experiment?
Depends. It's good to have, given that this is what we are measuring right now, it's good to have a lot of reactions and a lot of neutrons, because that means we get good statistics. When you're doing this reaction, of course, you don't want any of this at all.
I see. I see.
Yeah.
I see.
Right. Anyway, so gamma rays, if we look at that, this is my gamma ray spectrum for multiplicity 1 events. And you can see that there are peaks in here that line up really nicely with levels of nitrogen-14, as we would expect. I can shuffle through this at different multiplicities. So for example, multiplicity 2, this 3948 keV pops out because it likes to decay via 2 gamma rays. And I can shuffle through, and kind of by multiplicity 5, everything's gone. So I like to use this plot, this m less than 5. And so I've got all my peaks here, and now I can count them, and I can calculate a partial cross-section for each of these 4 excited levels. So if I do that, this is what I get. So in blue, red, yellow, and green, these are my partial cross sections, N1, N2, N3, and N4, partial cross sections to those 4 excited levels of nitrogen-14 in the carbon-13 DN reaction. So a couple things to highlight. We have actually extended down within the carbon-13 alpha and gamma window, which is cool. So I'd like to pat myself on the back for that. Oh, and I should mention I've included these points, this carbon-13 DN total measurement that Bruni and Kavanaugh did in 1992. I should also mention that the last point I was able to get the N1, N2, and N4 partial cross sections was this point here at 175. Unfortunately, I wasn't able to get it for these 3 lower points. But nonetheless, this looks pretty good. And as we should expect, for the most part, our reaction varies very smoothly, with the exception of this collection of points, which are all enhanced by about a factor of 3, which is very odd. And so the question that follows is there a resonance here in this reaction? And of course, what we should have done is we should have tacked over this range of energies with very small energy steps, and we could have nailed down the parameters of that resonance really well. We didn't do that. We didn't expect this to happen. I only noticed this as I was, wrapping up the data analysis. And now, of course, the facility doesn't exist currently, so we can't go back and do that. But nonetheless, if we think about resonances, as I mentioned, resonances correspond to levels in your compound nucleus. So for the carbon-13 plus D system, the compound nucleus is nitrogen-15. We know the Q value for forming nitrogen-15 in this reaction. And so we can do the arithmetic, take our deuteron energy of about 187 keV. That would correspond to an excitation energy in nitrogen-15 of 16,321 keV. And it turns out nitrogen-15 has a known level at about 16,320 keV. So it's not crazy that we might be seeing actually a resonance here. It lines up really nicely with this level. So it's certainly not, it's not outrageous, although unexpected. Now, if there is a resonance here, note also that the next resonance down in energy, there's a level in nitrogen-15 at 16.26 MeV. That would correspond to a deuteron energy of 115 keV in the carbon-13 plus D system. So if we're seeing a resonance here at about 187, there's no reason to say that there wouldn't also be a resonance at about 115 keV. And if I look at this comparison, yes, yeah.
So how big is the error bar in the previous figure?
Oh, and do you mean this one?
Yeah.
Yeah, the error bars are there are error bars on that. They're smaller than the markers, so you can't.
Oh, wow.
Yeah.
Okay.
And Chad, what about the black points are the total, right?
Yes.
What Bruni and Kavanaugh measured. So like you would sum all of your 4 points and then get that, I guess.
Almost, yeah.
Looks like
you'd be very close.
You would be close. Yeah, we were actually missing one partial cross section.
I see.
If you look at all these, right? If you look at all these subscripts, missing is the carbon-13.
Yeah, the 5.
Right.
Mm.
The ground state.
And not the ground
right.
state. Okay, I see.
Yeah, and that's because there's no gamma rays that come out of that reaction if it goes straight to the ground state. So we missed that completely. That's actually a big component that we don't have, and that needs to be done. But yes, if you had the ground state component and you added those 5 partial cross sections together, they should equal the total cross section measurement. Yeah. Anyway, so if I go and I compare, if I go back to this comparison plot and I draw 2 vertical bars at those resonance energies, should they exist, you can see that this makes a big problem even worse, especially for this lower resonance energy. That would be occurring in a region at which carbon-13 DN is already dominating, even at a very low contamination level. So yeah, so not only is this a big problem, this carbon-13 DN background a big problem that no one has thought about before us, but it's potentially even worse than we had imagined at first. And of course, future work needs to be done to actually get an even better handle on that. So anyway, that's all I had to show. So in conclusion, we have measured the carbon-13 DN1 gamma, DN2 gamma, DN3 gamma, and DN4 gamma partial cross sections at laboratory energies between 140 and 250 keV, which is, of course, as I like to toot my own horn, within the carbon-13 alpha and gamma window. So that's very cool. as Victor found, of course, an additional measurement of the D and naught partial cross section is needed. And I have ideas of how that could be done. But yeah, nonetheless, it'd be great if either our group or someone else went and did that.
I mean, you have the EJ301 data, so maybe.
Right. Yeah, that's true. We could use that. Yeah, right. So it could actually just be stuck in there too. That's not a bad, not a bad idea. But yeah, that's a missing component that either needs to be pulled out of existing data or needs to be remeasured. Otherwise, I mentioned that we see at least fleeting evidence of a resonance at a deuteron energy of 187 keV, and we of course recommend further study at smaller energy steps around that resonance should it exist at 187 keV. And if that resonance is confirmed, we highly suspect that there might be another down at 115 keV that would be worth looking at as well. Kind of the implications, of course, as I mentioned, beam-induced background from this carbon-13 DN reaction to your carbon-13 alpha and oxygen-16 reaction of interest, which is the actual cool one that matters astrophysically. You can quantify this background via the direct detection of gamma rays from the carbon-13, from the decay of nitrogen-14 made in the carbon-13 DN reaction. And kind of as a final sub bullet point, I say, I think the lessons learned from this work is be careful about how you are designing your experiments. Make sure you understand, everything, all the reactions, what's in your beam, what's in your target, and everything that could come out of the interactions of the two. Because if, again, you are underground and you're using one of these proportional counters, you have no idea how much of this background you're seeing. And you could be pushing into the Gamow window and you could be seeing a whole lot more of your background than your actual reaction of interest. So yeah, be careful, watch your background. Okay, of course, my collaborators, who I owe a lot of thanks to, a lot of very wonderful people who helped out with this work. Of course, you saw Mike Ferbaro's name popping up all over this presentation. So, of course, I owe a lot of thanks to him. Eli Timonson was a summer undergraduate we had in 2017 at Oak Ridge from the University of Wisconsin-La Crosse, and he did as much work as I did on the setup and running of this experiment. So he was fantastic, and he's now, I think, he's got to be in his third year of grad school at Florida State now. So yeah, as far as I'm aware, he's doing quite well for himself. But yeah. Oh, and I should mention, we had a ton of summer students help out with this. So that's really cool. Come to Oak Ridge and help out with something and get your name on a publication if you're an undergrad. It's my advertisement. So that's all I have to say. And thank you guys very much for listening, and I'm happy to take any questions.
So yeah, maybe let's unmute ourselves, or let's give Chad a big hand. Really cool. Yeah. Any comment, question? Yeah, go ahead.
Yeah, Chad, very cool talk. I enjoyed it. Just in the end, what you're revealing is really like how strong this background is, correct?
Right. Yeah.
And can I go back to the beginning of it, right? I was cooking while you were doing the introduction, so just like the general, like this reaction. Why is this reaction of interest? The carbon oxygen reaction. That's because it's that S process, right? Okay.
Right.
Yes.
Yeah.
Yes.
So
yes.
we believe it's the primary source of neutrons for this main S process.
I see. So you really want to understand all the resonances in there and all the kinks and
exactly.
nooks and crannies of that.
Right.
I see. Okay.
And we don't, and we don't at all. Right. We have no.
Yeah.
We've never measured this in the range of astrophysical interest. So we really don't know much.
That's very interesting. And then you're saying that if you were to go to this range of astrophysical interest, well, it'd be tough because there's a
Right.
huge background there.
Yeah. And the scary thing is
Oh.
no one's, as far as I'm aware, no one's thought about this before us. Everyone, everyone seems to have continued, seems to have pushed forward,
Yeah.
blissfully unaware. Maybe that's a good thing for them.
Well, I don't know.
But
The train,
not
the
for the
train goes
science, but
choo-choo.
for their own happiness, I suppose.
Exactly. The science the science train goes choo-choo and keeps going.
Right.
Doesn't stop. Yeah. Well, and at least from like an outsider point of view, from your data, it does look like there's a resonance there.
Yeah, it's
I mean, it's quite striking.
it is. Yeah, it's odd. If it were some other artifact, you'd definitely expect. Sorry, I got a lot of slides. You would definitely expect. It's odd to see all of them enhanced. That's a good tip-off that it's some nuclear physics going on, and it's not me making a dumb mistake in my analysis.
Yeah, that's true. Like if only the orange was going up, then there would be concern.
Right. Yeah. Exactly. And that's not to say I didn't spend a whole, I don't know, good 8 hours, 10 hours or so trying to make sure I didn't make a mistake there, and really combing through everything. So
only 8 hours, you're good.
Yeah, it might have been more than that. I definitely called up some people and had them, over Zoom, and had them like look at my calculations, and as I went through them, and make sure they didn't find me doing something dumb. So.
Yeah. Oh, really cool talk. Thank you.
Yeah, thank you. Thanks for listening in.
So I have a question. So like I think it's quite often that just you kind of build a machine or whole equipment just to finish one certain experiment, or is that just often happen in?
In nuclear physics, as far as accelerators go, no. I mean, these so Luna and Caspar, those are used, and they will be used for a whole suite of different measurements that are principally of astrophysical interest, but very low rate nuclear reactions. And so Luna's been in operation since the 90s, so they've got a whole bunch of publications out already on interesting things that they've measured. It's been a very active facility. This carbon-13 alpha N reaction is really sort of a holy grail of this kind of underground nuclear astrophysics effort. It's one everyone has wanted to measure, and no one's really done yet because it's really hard. So, but yeah.
Wow. Just curious, like, are there because like in condensed matter experiment, there are some people first, they build up some equipment, and later you'll find out that there are some commercial stuff, or some people go out to start a company and just sell some equipment, commercial.
Oh yeah.
Does that happen also in your area?
Yeah, we have commercial suppliers for a lot of the things, and it's sometimes we'll buy commercially, and sometimes we'll build our own. So like, for example, so I've talked about these neutron detectors, this EJ301D, that's a product name. So we buy, that liquid comes from Elgin is the company name. They actually do the chemistry, and they manufacture that liquid, and we can buy it from them.
Oh, I see. Well, the same. Okay.
Yeah.
Thank you.
But if we really felt like it, and we have in the past, I'm not a chemist, but there are Mike Fabaro, he actually has a background in chemistry, and Becca helps him out with this, and there are some other students at the lab who do this as well, that do this as well, and they have a whole chemistry lab where they make different types of detectors. So This is something you could do with some gumption. You could do this yourself as well.
Wow.
So it's sort of a trade-off between obviously the commercial stuff costs a lot more money.
Yeah, funding issue. Yeah, that's
right. It's usually overpriced compared to the raw materials, but for some things it's just so hard to manufacture that it's easier to let someone else do that and just buy it from them. So
yeah, cool.
There's a question from Rena on the chat.
Yeah, there's a question.
A chat which is why do experiments underground?
Yeah, so it's simple. It's a question. It's a question of background. So going underground really reduces your cosmic background, specifically cosmic. Any ground-based radiation is actually amplified because you have more ground around you, but it significantly attenuates the cosmic rays that reach your detectors. And you can see that here. So this is actually a plot. This is actually a figure in a paper by someone from the Luna collaboration. So this in black here, this is a gamma detector measurement. I think they're using a germanium gamma ray detector, but this is a germanium detector spectrum that they observe at sea level. And then if they bring that detector down to Luna, which is 1,400 feet underground, then they get this green spectrum. So you get a couple orders of magnitude at least improvement. And then you can do more fancier things and you can do even better. So yeah, really.
But later you say that Mike, he built up some experiments. So is that
right?
That it's how does that work in terms of this background things?
Yeah, so it's Becca might have a better handle on this. If you want to chime in. But
sorry, just can we repeat the question on that quickly?
Yeah. So
it was, yeah.
So how this? So Chad just say, okay, so this in underground is kind of significantly just lower lower the signal, the background signal, right? So when we're doing underground, but here next Mike, he designed a thing just above the ground, right, with some shield. And how this perform? I mean, how this compared to? Do we need to go underground or we just do this in?
So I think we were very optimistic when we first started trying to do this. We were like, if we just keep adding shielding, then it will get better. So that was basically what we did for the most part. So this slide is a really good example. We ended up using around 600 pounds of passive shielding, and then we realized that wasn't enough. So then we, but the thing is that as you add shielding, you reach like an asymptotic limit where if you keep adding it, it doesn't really give you any improvement. So we added in the muon vetoes, which gives you that that cosmic background suppression. But honestly, like there is no better cosmic suppression than just being underground. So we got enough suppression of the background to get the measurement that we needed, but to do better, which, like, let's be honest, we probably need to do, like, we did conclude in the end that we just need to go underground. Like, we did not get enough background suppression to be able to do more than we did. Like I said, it took a month to get enough statistics to do the last point. So it's just at that point, your every count is like a miracle. So it's like anything to make it easier. So
how about you do this underground? You do this and go underground. Combine the two.
We could. So that is something that we've been discussing with the people at Casper. They have, we've been in discussions with them about carbon-13 targets. So we found out that our targets were particularly durable, which is really good for these sort of high current experiments. So I actually went out to surf to Casper last November, I think. Or October or whatever, to take one of the detectors down there and see what the background looked like. So what is interesting is actually that there is while the neutron background is like incredibly low, it's like basically silent. It turns out that your gamma ray background is really high. So basically what we wanted to know was whether this gamma ray, we can obviously separate the gamma ray background using the pulse shape discrimination. But is that just going to give us rate issues? So, you know, it's like juggling a lot of different balls, basically, as it turns out. But
is an issue about that is because of the nature, the geological nature of where the site is. Some sites are like more gamma ray prone and some are not?
It's just the rock. It turns out like the rock is just like gamma ray radioactive, and it's fine when you're on the surface because like, you know, you've only got gamma rays coming from like below you, but once you go like a mile underground, you've got it coming from all four sides. And it's actually quite interesting because you see like
there's just natural radioactivity in the ground, and then there's just everywhere. It's just oh, there you go. There's just gamma rays. How about deep in the ocean? What about that? You could go a mile deep in the ocean.
Yeah, that is, I think, so there are,
let's build
I don't know if you guys...
a mile deep in the ocean.
Well, so I don't know if you guys are familiar with this, but there's a neutrino experiment called, I think it's called Ice Cube, which literally uses...
Yeah,
like,
in the ice.
Yeah, so that's like, yeah.
They're like,
we
they're
get
about
there.
that. They're about a mile deep into the crust of the Antarctica shelf.
Yeah, and there's another neutrino experiment, which is somewhere in the Mediterranean, which is just put a bunch of PMTs in the ocean and are just measuring,
it's cool.
which is really cool.
Yeah.
So
cool.
I mean, there's been crazier ideas than putting accelerators underwater because they're talking about putting them in space now, right? So
the
putting
new
them underwater
LHC,
would be easy compared to that.
You mean the new LHC, which is going to be at the Lagrange point?
Right. Yeah.
Wow. Okay.
But yeah, no, it turns out in soil and rock and stuff, there's a lot of thorium and uranium and radon and potassium, and you get more of that when you go underground.
Yeah.
Okay, so if we don't have any other question, then thanks chat again, and thanks so much, and thanks for you coming in.
Thank you, Chad.
Yeah, so I'll see you next week. Next week is our Victor actually. So
all right.
you can come here in our condensed matter theory talk. Okay, so thank you so much. Have a good night.
Thanks so much, everyone, for listening in.
Bye bye. Thanks, Chad. Bye bye.
All right.
Bye.